Welcome back. This is the last example for this week. So here you can see we have a motor. What does a motor do? What a motor does is you provide electricity into this motor, and then this motor will convert this electricity into mechanical rotation. This is what you see. On the left-hand side of the motor, you have electricity going in. That is my W dot in equal to -2 kilowatts. And then what comes out of the motor is on the right-hand side of the motor, which is a rotating shaft. So you can see W dot shaft is equal to 1,800 watts. Okay, so now here, why is W dot in a negative number? And why is W dot shaft a positive number? The reason is still the same as before. W dot in goes into my system, which is the motor. So that means the motor consumes W dot in. Consuming work, the work must be negative. And then W dot shaft comes out of the motor. That means the motor, which is my system, generates this work. Generating work means the work must be positive. Okay, and then usually the motor is really, really hot. So what's gonna happen is the motor is gonna lose heat to the environment, and that is Q dot. Here, Q dot is given as a function of time here in this equation, and the unit for Q dot is kilowatts. What we're looking for is capital E, which is total energy, as a function of time. And we also know at the beginning, when time is equal to 0, total energy E is equal to 0. Okay. All right, so we have some W's, we have Q dot, we're looking for E, and which equation goes to your mind? Which equation has W, Q, and E? Okay, the only option we have is first law. Q dot minus W dot equal to dE over dt. Right, because we deal with Q dot and W dot, so we choose option number 2. And before you use this equation, you should always check if your system is a closed system. And right now, my system is the motor. Is it a closed system? In other words, do you see mass transfer? Mass going in or mass coming out? And I don't see any. So yes, my motor is a closed system because there's no mass transfer. Okay. All right. Do we still have steady state? Be careful here. The problem doesn't say you have steady state. So that means the system may not necessarily be at steady state. Then you cannot get rid of the right-hand side, dE over dt. You cannot make it equal to 0 anymore. You just have to keep it. Okay, all right, so let's start. Let's see what we can do. Q dot, okay, I do have Q dot. It's given as a function. I can leave it. Minus W dot. Okay, just like before, how many W dots do we have for my system? I have 2 of them, so I have to sum them up. First one is W dot int. Second one is W dot shaft. And right hand side dE over dt. Okay, so now let's do plug and check. Do plug and check. All right, Q dot. Okay, let's move dE over dt to the left hand side. Okay, first term is Q dot. What is Q dot? Negative 0.2 times 1 minus exponential function with the index of negative 0.05 t. And be careful here because the unit is kilowatts. Minus the second one, W dot in. What is W dot in? Let's go back to the diagram. W dot in is right here, negative 2 kilowatts. Okay, so we plug in negative 2 kilowatts. And plus the third one, W dot shaft. What is W dot shaft? W dot shaft is given 1,800 watts. So what we need to do is we need to convert watts to kilowatts. So everything in the right hand side has the same unit. Okay, you can choose to use watts too, as long as every term has the same unit, then you're okay. All right, so the right hand side becomes negative 0.2 times 1 minus e negative 0.05t and minus plus zero point 0.2. Okay, and then we can take zero point 0.2 out of it. The only thing that's left is zero point 0.2 times exponential function negative 0.05t. Okay, so this step is simply algebra. Make sure you can do algebra. All right. Okay, and now take a look. dE over dt, still my left-hand side. What is this? What is this? This is an ODE, ordinary differential equation. So what we need to do is to solve this ODE. Do you remember how to solve this ODE? We need to do a separation of variables, meaning we move everything that has capital E to one side and everything that has t, time, to the other side. So what we do is dE is equal to zero point 0.2 times E negative 0.05t dt. Okay, that's it. So now we have separated the two variables. And then the next thing to do is to integrate both left-hand side and right-hand side. To integrate left-hand side, that is easy. Left-hand side just becomes E, capital E. Right-hand side, because zero point 0.2 is constant, you can take it out. So zero point 0.2 multiplied by integral E negative 0.05 t dt. So now we just need to integrate the right-hand side. Okay, this is pretty straightforward if you can remember what you learned in calculus class. If you don't, this is the reference. Integral E ax dx is equal to E ax over a. This is what you learned in calculus class. Okay, so now can you tell me what is the a for this problem? The coefficient before x is negative 0.05. So now this is easy. E zero point 0.2. So what is my solution? E negative 0.05 t divided by a, and what is my a? Negative 0.05. Okay, that's it. And now to simplify it, oh, don't forget, because we're integrating without limits, so you have to generate a constant. Okay, integrate without limits, that means you have to generate a constant to your solution. All right, to simplify, our solution is E is equal to negative 4 times E with the index of negative 0.05 t plus constant. Okay, how do we look for this constant? Usually we need initial condition. IC standing for initial condition. Do we have an initial condition? Yes, because we're given capital E is equal to 0 when time is equal to 0. So what we do is to plug in this initial condition back into this equation. Okay, left hand side, capital E, 0. Right hand side, negative 4 times E with index of negative 0.05 times T. What is T? 0. And then plus C. And from here, we can easily find C is equal to 4. And then finally, we plug in this C back into our solution. E is equal to negative 4 times E negative 0.05 t plus 4. This is our final solution. Okay, and the solution is in kilojoules. Okay, because we used kilowatts earlier, kilowatts multiplied by time, that gives you kilojoules. Okay, all right. So if you don't have an initial condition, you can just leave C in the solution. That's okay. If you don't have an initial condition, just leave C in your solution. Okay, that's it. That's everything for this week.